So, good morning, good afternoon, good evening, depends where you are now. So, today we are here to see another exciting talk by Professor George Gielen. But before giving the floor to Professor Sérgio Bumpi, that will be the chair of this session, just some brief announcements. So, next CASS talk will be in September 16 by Professor Said Hamdoui from Delft University. So the talk that we had scheduled for next week, by request of the speaker, it will be moved to later this year. So the talk by Said will be device-aware test, the mean to win the war against unmodeled faults. Then the week after, we have a Professor Jan Madsen from Technical University of Denmark talking about biocomputing, computing with biological circuits. October 7 is Professor Chokaridis from University of Cyprus talking about bio-inspired joint hardware and algorithm acceleration for edge computer vision. Then October 14 is Dr. Alan Mishenko from University of Berkeley talking towards next generation logic synthesis and verification. Then the talk by Professor Jan Okorno, it's moved to November 25th, and it will be about emerging technology-based 3D compute cubes for edge intelligence. So if you lost one of the CASS talks in these last 3 years, you have the recorded versions available in this YouTube channel. Next week, we have a IEEE Sequence and System Society tour in Argentina. So the tour will be, here there is a change in the slides. So October 6th will be in Cordoba. But before this, next Monday, September 5th will be in Buenos Aires. And then from 7 to 9, it will be together with Argencon, that is the IEEE conference in Argentina. So having also talks by Manuel Delgado Restituto, that is the president of CASS, and Victor Greenblatt. And in all three locations also talks about the opportunities in international insertion when being an active member of IEEE CASS. So it's open the submission of posters for the sixth seasonal school on digital processing of visual signals and application that will happen in November 16, 18. Then you have the still open the call for papers for Alaska's and Iberchip in Primary A that will be co-located in Quito, Ecuador, end of February. And there is a path to have best papers of Laskas in TCAS 2 and TCAS 1. The one selects for TCAS 2 will appear in the edition of the months of the conference. So in the proceedings, we are going to see only the abstract of these selected papers. Then, considering also the presentation at Laskas, there will be another selection to invite authors to submit extended version of their best papers to TCAS 1. So this will be a very interesting opportunity to come to South America and to see a very nice location and participate into a very nice conference. Then next year, you can put in your agenda, ISVLSI is coming to Brazil, to Iguaçu Falls, from June 20 to June 23. So you'll be also another very nice conference in a very nice location. So, but today we are here for the talk of Professor George Gielen. So Professor Sérgio Bumpi will be the session chair. So I give the floor to Professor Sérgio Bumpi to chair the session. But before that, I would like to thank again to George Gielen to accept our invitation, as well to Professor Cecil Bumpy to accept to be the session chair of this interesting talk today. So, Bumpy, the floor is with you.
Okay. Thanks, Ricardo. It's a pleasure for the chapter of Secret and Civil Society in Rio Grande do Sul to host once again Professor George Gielen. He has been in the South America region and visited several chapters over the years. He's a very experienced designer, as you can see. George Gielen is a fellow of IEEE. He has been president of our Secret and System Society also for a few years. He has been in the field for more than 35 years, as you can see, holding a master and PhD from Catholic University of Leuven, where he's now professor, and also head of the electrical engineering department, the ESAT department. And he has been working for this more than 35 years in the MICAS, which is a very active group in microelectronics, both digital and analog, covers several fields in our secrets area. So, it's our pleasure again to host you, George. We consider you a good friend of people here in the Region 9, the Latin American region of IEEE, and hosting a fellow and experienced person like you. I'm pretty sure that everyone in the chapter, everyone in the audience here at YouTube will enjoy. If you have any questions to Professor Gielen relating to this talk or anything in microelectronics, just type your question in the YouTube channel, and at the end, he will address your question. Thanks a lot, George. Welcome back to even virtually to South America, but we're very pleased to have a good friend and such a great researcher and great person with us again. Thanks a lot.
Okay, thank you very much, Professor Bumpy and Professor Reyes, for the invitation. As was said, it is always my pleasure to come to Latin America and to establish the contacts with the CASS chapters and the university groups over there because of the high quality of the research and education that is being done in these institutes. Um, I am now starting the presentation.
It's not appearing yet. Ricardo, do you have to bring down the poster? Okay,
Yeah.
thanks. It's up. It's up and running. Thanks, George.
Okay. And so this presentation is about sensing interfacing in the edge. And it has as a subtitle Small, Sound, and Smart. And I said before, I'm at the university in Leuven, also called KU Leuven. And if people are interested about this work, at the moment you can type your question in the chat, and later on you can mail me at gielen@kuleuven.be. But of course, the question is, where is Leuven? And in case you don't know, we are here. Where, as indicated by the top red arrow, and Porto Alegre, sorry for the typo, is down there in the south of Brazil. And as you can see, it is quite some distance from each other. And in normal circumstances, I would come and give the seminar on site. But in these post-pandemic or hopefully post-pandemic times, it's still not easy to travel. Now, before starting the actual seminar, just a few pictures from Leuven itself. Leuven is a small city, and here you see the city hall, you see the main library, you see the central square, and you see even a castle from the university, all in the small city of Leuven, which is about 30 kilometers east of our capital city of Brussels. The nice thing about Leuven is that it's a university town. That it has 100,000 inhabitants, and on top of that, it has this university with locally in Leuven 45,000 students. So you can imagine that 45,000 students in a town of 100,000 permanent inhabitants. that this gives a very lively city with lots of actions going on during the day, but also during the night, except for the exam periods when it's quiet all over. Now, at this moment, the percentage of students at Leuven University that is international is 16%, 16%. So that is quite high. So we focus a lot on having international students, exchanging students, and so on, mostly at master and PhD level. But back to the talk. The talk is about sensing, and I will first start with a brief introduction about sensing in the smart world. And then I will explain some way how we can make this sensing small, how we can make the sensing sound in the meaning of robust, how we can make the sensing smart, and then I will end up with some conclusions. So today it's clear that sensing has become ubiquitous in our society. In almost all applications, we use more and more sensors. Think of healthcare, where people today have a Fitbit or a watch, a smartwatch, to measure some of their biomedical signals. We have domotics in houses to control energy, to control lighting, etc. We have cars that have a lot of sensors, including cameras, of course, radars, etc., to find the optimal positioning on the road, to detect if there are any other cars nearby, any other pedestrians or bikes nearby, etc. We use a lot of sensors in industry, in consumer applications, and in infrastructure. So in all these applications, you see that there is a growing use of sensors. And what we also see today is that these sensors, in an increasing way, are networked. That means that they are somehow not just sensing, but they are connected to the internet or connected to the cloud, as you can say, and they send their sensing data to the cloud. And the second evolution is that people want not only the sensing nodes to just transmit data, but that they want the sensing nodes to do smart processing, to have some kind of intelligence to process the data locally. And that is very important. I will come back to that later in the talk. But first, some market figures. So on this slide here, you see from this market analysis, you find the source there on the slide, the growth of the IoT market in the past recent years. So despite COVID, you see that there has been a significant growth from 2016 to 2020 in IoT, with growth rates that are approaching 40%. Now, a market that has 40% growth rate, that's enormous. And if you see in this figure from the same organization, you see in which areas this growth is realized. And then you see that 24% is industrial IoT applications, 26% is in smart cities, meaning monitoring in cities. 20% is in connected health devices connected to the internet, 14% in smart houses, 7% in connected cars, and so on. So the main drivers are smart cities, industry, health, smart homes, and automotive. Now, if we look at all these applications, what are the requirements? Well, of course, it's clear that, first of all, we need to have the requested performance. Secondly, many of these sensing devices are operated on batteries, So the power or the energy that they consume has to be extremely low, because we cannot, in all these applications, we cannot always replace batteries continuously, and we can also not always recharge batteries every evening in many of these applications. A second requirement besides performance and power is reliability or robustness. Many of these applications, especially if we install them in the field, many of these applications must keep on working even if the temperature rises to 40 degrees in summertime and goes below zero in wintertime, etc. They must be always working as expected. So reliability or robustness is a key. A fourth requirement is the cost. So for many of these applications, to really make it to the market as a realistic and ubiquitously used application, is that the cost of the sensing must be very small. Now, for sensing nodes that are based on chips, it means that the area of the sensing node must be very small, because the area is a large contributor to the overall cost. So these are the main requirements: performance, low power, absolute reliability, and low cost. And as I said, in recent years, there is also the requirement to be smart or intelligent, meaning that they should not just sense signals, create data, and transmit data, but that they should also do some processing on the data and only transmit information. Now, in my research group here in the MICAS division of our university, we are doing research on many different application fields. And I show here two examples of chips that we have designed in recent years. One is from the automotive field. So this is a sensor targeting to be used in cars for reading out sensors in a car. And it was designed by Elisa Sacco, who actually graduated with her PhD 2 days ago. And she designed this chip in 2019. And we were able to show that with this chip, we can achieve 16.1 bit of resolution. And okay, that is not the surprising thing. The surprising thing is that we can do that in a small area of only 0.64 square millimeter. And later on in the talk, I will explain how we can achieve that, how we can achieve such good performance in such a small area in a technology node that is 0.18 micron CMOS, so 180 nanometers. So that's really not a very small technology node. So it does not come from the technology, it comes from the smart design that we use. Second example is in the biomedical field. We also do a lot of research in biomedical chip design, and here the application is neural recording and stimulation. The whole idea is to make a device that you can stick in your brain to record neural signals and potentially also to stimulate neurons. And of course, the whole idea on the longer term is to build a closed loop system that can record and stimulate when needed based on the data from recording. And this is a project that has been running for quite a while. And you see here one of the early designs that we made. On the left, you see, as indicated with the dashed lines, you see the probe shank, so the shank we stick into the brain. and then the probe body, which is where the electronics is to read out the signals from the electrodes. The electrodes are on the probe shank. We then have lines connecting the signals to the probe body, and then the probe body itself is zoomed out on the right figure there, where you see first the amplification and the filtering stages, and then the A to D converters, the analog to digital converters, to digitize the signals. In this particular design, we were able to have 455 electrodes on the shank, and at any moment in time, we were able to read out 52 of these electrodes. In the meantime, we have made other designs where at this moment we have been able to read out more than 1,000 electrodes simultaneously. One of the things that has to be remarked here is that for every channel to read out a signal, we consume 17.8 microwatt, which is rather on the high side. So later research has also been working on reducing the power consumption by these recording circuits. And by the way, besides the 52 recording electrodes, we also have 13 stimulation electrodes on the same chip, obviously on the shank. Okay. So these were two applications that we have designed, and both were published in the Journal of Solid State Circuits of IEEE. And I will now explain how we are able to make such sensing interfaces small. If we think of analog circuits, why do analog circuits, why do they have a certain area? Why are they as large as they are? Well, this of course depends on the requirements that we pose on the circuits, and the main requirements are the speed, the accuracy, and the power consumption that we allow for the circuit. And as we know from the publications of Professor Eric Vcos, we know that an analog circuit suffers from thermal noise. And in order to overcome the thermal noise with a certain dynamic range, we need a certain power consumption at a given frequency range. So the exact equation is shown there on the top here. The power is 8 kT times the frequency times the requested dynamic range. So that means that in order to achieve a certain dynamic range, we need especially capacitors with a certain area so that the integrated noise meets the dynamic range requirement. So that means that in order to get to the requirement of dynamic range, the area needs to be a minimum big size. And of course, when we talk about sensing requirements and we talk about dynamic ranges of 16 bits and more, 16 bit is quite a lot. The noise has to be quite low, which means that the capacitors has to be quite large. But there is another reason why the analog circuits need a certain area, and that is the mismatch of the devices. Devices can be transistors, can be resistors, can also be matching capacitors. And so for all these devices, when we fabricate them in large volume, they have a certain mismatch. This mismatch translates in a certain offset, in a certain error on the accuracy. And again, in order to obtain or meet your requirement in terms of dynamic range, your offset must be low enough And this can be achieved only when your devices are large enough. So again, in order to achieve your 16 bits or more of dynamic range, your offset must be low enough, which means devices of a certain large area. And the exact equation is shown there. I refer to the publications of Professor Peter Kinget from Columbia University, who actually did his work in our group in Leuven when he published this for the first time. So whether it's noise or whether it's mismatch, they both have the same consequence, is that if you have a certain speed requirement and a certain maximum power, and you want a certain accuracy, then that implies a certain minimum area in order to meet that combination of requirements. Now, if you need a certain minimum area of requirement, if you need a certain minimum area in order to meet your requirements, but your technology gets smaller and smaller, and your analog circuit still need this minimum area, then there is a financial problem, because your more advanced technologies, they become more expensive. The circuits themselves should become cheaper because you scale the circuits, but I just told you that for the analog circuit, the scaling is not true in the same way. You can't make them smaller, because then you cannot have your dynamic range requirement if your mismatch, if your matching does not improve much. So that's why the analog circuits do not scale well with scaling technology, and therefore your cost does not go down. So the question now is there no alternative? Is there no other way to get out of this lock situation? Well, it's clear that as long as we stick to signal processing with signals represented as voltage, we are stuck by what I just explained in my previous slide. But there is one alternative, and that is that we can represent signals also in the time domain. And by representing signals in the time domain, we can overcome this limitation. We can then fully take advantage of the fact that with progress in technology, the timing resolution improves. And since we represent the signals with time, and timing resolution improves, we can make smaller circuits that still meet these tough requirements for the analog sensor interfaces. So the whole idea here is that, okay, we can do it if we convert the sensor signal to time signal or frequency signal, and then we digitize that. And then we still have our digital sensor signal at the output. The question now is, how do we do that? Well, the basic architecture, one of the possibilities, but the very basic architecture is shown here. So let's assume, as an example, I will show some other examples later on. As an example, let's assume that the sensor is a capacitive sensor. So it's represented here as a capacitor with an arrow, which means it's a variable capacitor depending on the physical signal that you want to measure. How can we convert that capacitance from that capacitive sensor into a frequency or a time? We can do that by putting, for instance, the capacitive sensor as load in a ring oscillator. If the sensor signal changes, then the capacitance changes, then the load changes, and therefore the frequency of oscillation changes. So in this way, we can convert the physical signal to be sensed into a frequency or a time signal. Step 2 is then to digitize this. How can we digitize this? Well, this can also be done by using a very similar oscillator, ring oscillator, which is shown there on the right, called oscillator digital. This oscillator is identical to the first one, but it has now a capacitive load in one of the stages with switches. So it can be, and these switches are controlled by the digital signal B out coming from the output of this circuit. So this digital signal controls the switches, and by closing a switch, you add more capacitance to the node, changing the frequency, or by opening a switch, you reduce the capacitance and you also change the frequency of oscillation. Okay, so in this way, we can create a digitally controlled oscillation frequency. And in order to read out the frequency of the sensor oscillator, we put an extra block there, which is called PD, Phase Detector, which takes as input the output of the first oscillator and the output of the second oscillator and compares the phases of the two signals. This is put in a feedback loop, and because it's a negative feedback loop, you can understand that equilibrium will be reached when the input to the phase detector will be equal. Now the input is the phase, so that means that the equilibrium will be reached when the phases of the two oscillators are equal. Now, the phase of the sensing oscillator is determined by the sensing signal. That means that due to the feedback, the output of the phase detector will be steered through this feedback mechanism, will be steered such that the digital oscillator also runs at the same frequency as the sensing oscillator. And when that is the case, then the output of the phase detector, the digital output B out, is exactly a digital representation of the sensor signal, of the frequency of the sensing oscillator, which was depending on the sensing signal that was steering the capacitor. Okay, so in this way, with the first oscillator, we convert sensing signal into a frequency, and then with the second oscillator and the feedback loop, we can digitize the signal towards the output. Now, what is interesting with this structure is that you read out and digitize an analog signal. But if you look at the architecture here, what do you need? You need one oscillator, that is a ring oscillator, a couple of inverters with some feedback. And you need a second oscillator, a couple of inverters with some feedback, and you need a phase detector. Phase detector is also a digital block. So I am creating an analog function to read out an analog signal, but I'm using mainly digital blocks. And therefore, because it's mainly digital blocks that I'm using, I can achieve a small area, and it can become scalable with technology. When the technology node shrinks, the digital blocks can be smaller, and therefore you can make a smaller sensor interface. Second advantage is because you use two identical oscillators, the sensing oscillator and the digital oscillator. Any phenomenon, any effect that affects the two oscillators in the same way, in other words, that is common mode, for instance, any change in supply voltage or any change in temperature, as long as it's common mode, so equal for both oscillators, it will affect both oscillators largely in the same way, and therefore it will not change the output. So you can say that this is, by construction, very robust for common mode errors. And then a last benefit is that if you look at this structure, then you see a phase detector that is taking the difference between two phases. So it's a delta function. And if you look at the oscillator, then we know that the input controls the frequency, but at the output we use the phase. And we know that the relationship between phase and frequency is an integration. Therefore, implicit in the oscillator, we have an integration. So this structure actually has a differentiation and an integration. So in other words, it is similar to a delta sigma converter, be it that it's not in the voltage domain, but in the phase domain. Now, if it's similar to a delta sigma converter, it also means that when we use oversampling, we can increase the resolution or reduce the quantization noise by using oversampling, and by playing with the noise shaping order, we can reduce the quantization noise even further. In the structure that is shown here, we have a first order delta sigma modulator, because the conversion from input signal to frequency and then frequency to phase, that's one integration, but we can add a second and a third order structure by making the circuit more complicated, and then gain even more in terms of signal to noise ratio. So this is the basic principle. By using oversampling, we can further increase the SNR. So what is then ultimately limiting the SNR? Well, obviously that will be then not the quantization noise, but the thermal noise. And in this case, the thermal noise reflects as phase noise. Phase noise in the two ring oscillators or Vcos that we are using. And the graph shows indeed the maximum on the y-axis, the maximum achievable signal to noise ratio as a function of the PN. PN stands for phase noise, as a function of the amount of phase noise on the x-axis. And this for different values of oversampling ratio. So the different, as you see on the legend on the top right, the different colors of the curves correspond to different amounts of oversampling ratio. So the dark blue curve is the bottom one here, has little oversampling ratio. So that means that its maximum SNR will be limited to 40 in this case. And then from a certain phase noise level on, it will be limited further by the phase noise. If we take the red curve, for instance, the oversampling ratio is 5,000, then you can see that the maximum achievable signal to noise ratio due to quantization noise, that the limitation is not even visible on the graph, and that the entire limitation comes from the phase noise of the oscillators. So the phase noise ultimately limits here the SNR in practice. Okay, based on this concept, we then designed several chips to demonstrate that this mechanism works in practice. Here you see the plot for a capacitive time-based sensor interface, basically the principle that I showed before. It was done in an advanced technology 28 nanometer, operating at 0.5 volt. And you can see that the area is extremely small. It is 0.0045 square millimeters. So 0.0045 square millimeters. Very small area for this sensor readout. And that is because of the highly digital nature of the structure. Now, the same concept can also be applied not only to capacitive sensors, but also to resistive sensors. In this case, you see the structure here. The resistive sensor that you want to measure is now put in a kind of Wheatstone bridge configuration, as you see here in the circuit on the left. and we tap the two midpoints, and we feed them as controlling node to a VCO, one being the sensor VCO for the tap point that is connected to the resistive sensors, and the other one feeding to the loop VCO from the tap point of the digitally controlled resistor. The two digitally controlled resistor branch to the two resistors there. They are controlled with switches, and the control comes all the way from the right, and the right is the output again of a phase detector that compares the phases of the two oscillators. And so the circuit works in exactly the same way. If the physical signal that you're measuring changes, then the resistors change, then the bridge gets out of equilibrium. The two VCOs will be operating at a different frequency, and then the digital feedback will bring the circuit back in equilibrium. And so the digital output that is needed to bring it in equilibrium will then be a digital representation of the sensor signal. And so we built a second order structure like that. And in this case, it was done in a standard 130 nanometer technology, more standard for sensor applications. Later on, we have also implemented the same concept of readout structure in carbon nanotube technology, not in a CMOS technology. And the main reason for this is that if you implement your sensor readout as a digital circuit, then of course the amount of power that you need depends on the energy delay product of your digital circuits that you are using. And the carbon nanotube transistors happen to have an energy delay product that is 10 times or more better than silicon CMOS in scale technology nodes. So because they have a better energy delay product, it also means that we can make sensor readouts that consume less power for the same performance and speed as the CMOS equivalent. And then in collaboration with Stanford University, in the labs of Professor Wong and Professor Mitra, we have then designed a couple of sensor readout circuits that demonstrate indeed that this is the case, using these carbon nanotube transistors for which in Stanford, they master the technology. And here you see some results. For instance, we built infrared readout circuit. So a readout circuit for infrared sensors using the same concept that I explained. And using a 32 nanometer CNT technology, the power consumption in this case is only 130 nanowatts. So a very low power consumption to read out this sensor. And the second advantage was that we did not need a separate infrared sensor because the carbon nanotube transistors themselves were the sensors. So carbon nanotube transistors are sensitive to infrared light. So if you allow them to be exposed to the infrared light, then they get influenced by the infrared. They change in a ring oscillator. They change the frequency because of that, and we can read that out. So we didn't need an extra external sensor. It was all in one and the same carbon nanotube circuit. Okay, so to answer the question, how can we achieve small analog sensor readout circuits? Well, the answer is don't design them as analog circuits, but use digital-like or highly digital structures that are scalable with technology, and that can be made very small. Secondly, use oversampling. Sensor applications that normally have a low bandwidth, so that means that we have plenty of frequency margin to exploit oversampling. Thirdly, like I said, we can also use nanotechnologies like the carbon nanotubes, but also we can use 3D stacking to have some CMOS with some sensing levels on top and so on. And a fourth possibility I did not explain, but we can also, instead of making every sensor individually very accurate, we can also make them inaccurate, but use many of them, and the combination of these many can be made very accurate at the system level. So in that case, we exploit the redundancy to be more accurate at system level, not at the individual sensor readout level. So this was answering the first part, how can we make them small? Now comes the second part, how can we make them robust? Because robustness is very important in sensing applications. Take again the example of the cars in automotive. The requirement is that sensors must operate from minus 40 degrees centigrade to plus 175 degrees centigrade. That's quite a large range of temperature. They must also be robust to variations of the supply, in this case the battery. We know that the battery voltage is not constant, it fluctuates. When the battery gets older, voltage goes down, etc. So it must sustain all these things and still keep the same performance. So how do we do that? Well, we do that by three things. First, we look for a sensor readout architecture based on the same concept that I explained before, using these oscillators that we bring in phase with the phase detector. But we make some changes to the architecture such that it is robust to variations. And the first change is here that we, for the resistive sensor, we put the two sensor resistors in the bottom and we steer them with two current sources instead of with resistors. And these current sources are then digitally controlled from the output. And the advantage of that is that the change of, as you see from the equation on the right, that the change in resistance due to the sensing signal variation, that change relative to the nominal value of R out is depending on the ratio of the LSB current of these current sources to the nominal value times the digital code. And so this ratio of currents is quite constant, quite stable with temperature. So we already start with a quite stable thing. And then we have this common mode reduction due to the two oscillator and so on. And so that gives us a high suppression of common mode errors. Secondly, that suppression of common mode things is true, assuming that the two oscillators would be equal. Now we design them equal, but of course in fabrication they will not be equal. There will be mismatch. And whenever there's some mismatch between the two oscillators, the suppression of common mode errors will not be perfect. Now, in order to overcome that, what we do is we do chopping. So we chop the two oscillators, and because we have an operation in the time domain, we chop the two oscillators in the time domain, meaning that we alternate over time the connections of the two oscillators, and we do that before the two oscillators and we do that after the two oscillators. And this then reduces the impact of mismatch on the two oscillators, and at the same time it also reduces the impact of 1/f noise. So the flicker noise of our transistors, which is present at low frequencies, will also be suppressed by this time-based chopping. Now, when we did the analysis, we found that this chopping alone does not reduce all the errors due to mismatch. And therefore, we needed a third technique, and which is the tuning of the Vcos. So we do a tuning of the one of the two Vcos to make, for instance, its nominal frequency equal to the other oscillator. And then after this tuning, in combination with the chopping, we are able to cancel to a large extent all the effects of this mismatch, and therefore we can achieve a good performance and suppress well these common mode errors. So these are the three steps: an architecture that by itself has a good temperature robustness, a chopping, and a tuning. And based on that, we developed a time-based sensor readout chip that was achieving 15 bits of resolution. And on the figure on the right, you can see that indeed the yellow result, the yellow spectrum, shows no or little impact of 1/f noise, while the blue spectrum without chopping and without tuning has this 1/f noise impact. And the same is true for the spikes, the distortion spikes that you see there. So in this way, we have been able to show that we can make a circuit that is robust with respect to 1/f noise. And here you see the measurement with respect to temperature. So the x-axis here is temperature -40 to +175 degrees. And you have to look at the curve with chopping. The blue curve shows the offset error. You see it's almost on the zero line here. And then the red curve with chopping shows the gain error, and you see that it's very much reduced across the entire temperature range. And the actual values is 0.3 ppm per degree centigrade of offset variation over the entire temperature range, and 2.3 ppm per degree centigrade for the gain variation across the same entire automotive range. And so these performance values show that this kind of circuits, analog sensing readout, but using highly digital architectures, that these kind of solutions can be very robust with respect to all kind of variations and processing imperfections. Okay, the last part of the presentation is about how can we make the sensing readout now smart. Why do we need smart readout? Well, I told you that traditional sensing was collecting data. When we connect the sensor node to the cloud, it was transmitting these data to the cloud. But you can imagine that with the growing number of sensors that are connected to the cloud, this is enormous amounts of data that are being transmitted to the cloud. And this will saturate completely the communication channels, and it will also consume a lot of power to collect and transmit all the data. That is why people today ask for not bluntly transmitting all the data to the cloud, but to do local processing of the data at the place of the sensor node. So we call that at the edge, because the sensor nodes are at the edge of the cloud. So we call that processing or computing in the edge. And when you do processing in the edge, it means that you locally process the signals, and then you can also introduce some techniques of machine learning to not only process the data, to compress them, but also to do a local decision making, to do learning in the edge, and so on. And a recent study of McKinsey for instance, showed that this whole market of edge computing by 2025 is estimated to be about $200 billion. So $200 billion is quite a nice market. So what do I mean with this edge computing? Well, I have been talking about reading out the sensor and conditioning the signal and digitizing it. So we can do we can build intelligence into the sensor readout, which is the first part. But then on the digital data, we can feed them also to some local processor or maybe a local neural network or something like that to also take local decisions. And then we talk about embedded edge processing. So we can build in the intelligence in the sensor readout and do local processing before we transmit the resulting data to the cloud. Or for autonomous applications, we then even don't have to transmit it to the cloud. We can do it fully autonomously in the device. For instance, in autonomous robots, as was shown here, in a disaster environment or in a forest fire environment, in the rainforest in Brazil, there we can use such autonomous devices. Okay, a few examples from both cases. So first, optimization in the front end. If we look at, for instance, here, biomedical applications, if we look at the ECG signal, then you see that the information, which is the left signal there, signal on the left, you see that the information is actually in the peaks and in the repetition rate, the beat, the repetition beat of this heart rate signal. But in between, there is less information. So that means that we do not really need at high sampled rate the signal, but if we get the main information about are the peaks okay and is the rate of the peaks okay, then we have all the most important information for medical purposes. Same here when we have in the third plot, when we have the a neural a readout for neural signals, neurons in our brain, then the information is maybe in the low field potentials, but then the other information is in when is there a spike, and in between spikes, there's just some noise. So the signal is not in sampling and digitizing the signal on a continuous base, but it's in the spike information. And so that means that in all these applications, the actual signal bandwidth from a signal theory point of view is quite high, but the information rate is quite low. And so if we can build a structure that looks at the information rate and not the signal bandwidth, then we can save a lot of power, and we can reduce a lot the bandwidth of the data, the amount of data that we need. So this can be done in different ways. One is to use compressed sensing techniques, where we first digitize the signal in a standard way and then kind of compress the data by applying some kind of transforms. In this case, the example shown here is a ECG, so the heart signal, where we apply the discrete wavelet transform that can then reduce the data to a lower representation. This lower representation can be transmitted to the cloud, and as shown here in the bottom plot, after receiving it from the cloud, the original signal can be reconstructed without significant loss in fidelity of the signal, and we actually only transmit 8% of the data. So we do a compression of 92%. With only 8%, we get the same information across the cloud. Another way to reduce the amount of data is to use event-based sampling. In this case, instead of sampling at the highest frequency that is present in the signal, we sample it at a lower rate, for instance, a rate that depends on the activity of the signal itself. So the figure on the left shows you on the top a fixed rate sampling, and at the bottom you see that it only samples when the signal changes a lot. So if the signal changes, it will sample more. If the signal kind of stays constant, it will sample very little. And in this way, okay, we have a variable sampling rate, but for signals that remain steady for quite some time during their operation, and we have seen that that is the case for the two biomedical applications that I explained, the heart signal and the neural signal, then we can save a lot of samplings, and therefore we save data and we save power. So here you see the results. So we save power, which means that the power consumption from the A to D converter that is needed to digitize the signal can be a lot lower than with the traditional Nyquist sampled A to D converter. And secondly, we also save power at system level because you have less data that needs to be transmitted to the cloud. And if you need to transmit less data, you also save power at system level. The structure that we use to do these experiments with here is the structure shown here on the right, which is a level crossing A to D converter. And actually, at the end of this month at the ESSERC conference, my PhD researcher, Jona van Asse, will present the design that he made, the chip that he made in order to demonstrate this functionality and the benefits from this level crossing A to D converter that you also see in these plots here. The second part is, okay, now we have our digital data. What do we do with that? Well, we can feed those data to a neural network and then have that neural network take some decisions locally in the edge. For instance, as shown here on the left in the plot, this is the Castle of Angels in Rome. And if you take the picture, we could digitize every pixel individually, we could compress the signal and so on. But what we are interested in is not so much the compressed image, we are interested in what do we see in the image. And so if we have a neural network that can recognize persons or statues or other objects in the image, then the neural network can identify those objects and feed that information either locally to the robot or send that to the cloud. And so here you see with the boxes indicated what are the different objects that are recognized by this neural network. Okay. Now, the traditional way to do this kind of object recognition would be to use a deep neural network, meaning a neural network with many layers of neurons. Now, we want to put this neural network in a sensing node operated by a battery where the power consumption should be low. Obviously, when we do this with a deep neural network, this will take a lot of power, and therefore our battery will be gone very soon. So that is why we have been looking at alternatives that do not use this deep neural structure, but that can do the same performance, be it in a different way with a lot less power consumption. And we have been working on doing this neural network in the edge using spiking neural networks. And so here you see some results of where we do the readout of the radar that is used in a drone. So we have a drone with a radar. We read out the radar signal to autonomously steer the radar. To autonomously steer the drone. So the drone will move around in a room or move around on the street, and it will see if there is an object from the neural network that is embedded in the drone, and this neural network is a spiking neural network. You see the structure here at the bottom. We use integrate and fire spiking neurons, and we have 1, 2, 3, only 3 layers of neurons. So it's not a deep neural network. It's only 3 layers. And the whole clue to make this thing equally functional to a deep neural network is to do the proper pre-processing of the signals. So we have some pre-processing of the radar data. So the data that come directly from the radar, they are pre-processed and then sent to the 3-layer spiking neural network. And then you can see from the results here that with the proper setup and the proper tuning of the spiking neural network, you see that in the second table, encircled by the red line, that the neural network, spiking neural network, achieves 93% of object recognition accuracy, while the best deep neural network that we use as a reference, which is shown in and encircled in the top table, also achieves 93%. So you see that the deep neural network and the tuned spiking neural network can get to the same performance level, same accuracy of object recognition in this case. Okay, and what is the benefit? Well, the benefit is that the spiking neural network has only 3 layers plus some pre-processing, so it's very small, and therefore it consumes very little power. And as shown here, it's estimated to consume only 2 microjoule of energy per inference, per decision on object recognition on a chip, a spiking neural chip that has been developed here in Leuven by our university in collaboration with IMEC, called the microbrain chip. And the same results have been achieved by other authors. So not only here in Leuven, but also by others. Here is an application of such a spiking neural network chip, preceded by an analog to spike converter, followed by a spiking neural network, and then an event-driven communication to the cloud for cardiac monitoring, so monitoring of the heart. You see that if you transmit, so on the top right, you see 3 bars. The higher the bar, the more the power. And you see that the first solution, transmitting using a standard A to D converter and transmitting all the data to the cloud, has a high bar. Doing local processing and process the data with a local DSP even consumes more power. And what you see is that with the local spiking neural net processing, the bar is a lot lower. So you need a lot less data, a lot less power consumption in this case, and you also send less data across to the cloud. So you also save data power at system level. So I conclude here that sensing, and especially network sensing, has become ubiquitous today in all kinds of applications, and that the recent trend is to not only do sensing and readout, but to also do local computing in the edge in order to limit the data, to limit the power consumption, and also to limit the latency in some time-critical applications. In terms of cost, because of cost, this requires miniaturized sensor interfaces, and I have explained to you a technique how we can use highly digital, time-based solutions in order to reduce the area of the readout. It results in small area, but also in CMOS scalability and high power efficiency. I've also shown that we can make these circuits ultra reliable. So doing it this way does not sacrifice the robustness of the solution. And then finally, I've shown to you how we can build in intelligence in the edge, both in the processing that is done in the analog part, as well as in the local processing of the digital data with neural net technology, where I've shown that, for instance, spiking neural nets are a very good alternative to the standard deep neural networks. So that brings me to the end of my presentation. I, of course, have to thank all my PhD students who have done all this work. And I have to thank my collaborators and my funding organizations. And I said, if you want to contact me, you can do that at this email. And that brings me to the last part, which is up to you to ask me questions.
Okay, thanks. Thanks very much, Professor George Gielen. That's an excellent, overview of so many threads of this subject, from circuits all the way to system solutions that are very creative and very innovative. Well, I'm looking here at the people in the YouTube channel. You can, go to the YouTube channel of our chapter and ask any questions. I have a few questions. Okay, you have done such a great, guided tour to so many issues. Let's start from the back, from the more system level on cognitive sensing systems. So can you tell us more about this microbrain chip project? Because on the slide on the 2 microjoules for inference, where you do use the time to first spike solution in this chip, here lies some digital blocks to assist the analog processing, or is this chip entirely dedicated to the neural net processing? Basically, where in the microbrain chip is sitting the front end that you referred to, the analog front end?
Yeah. So what you need is you need for an application like this, as shown here, you need a radar and a radar readout. So from the radar chip, we already receive digital data. So the analog front end in this case is you have to see this is a commercial drone. We use a commercial radar readout chip, and there are digital data coming out. These data are being processed locally with 2 pre-processing steps. The last one does also some spike encoding, and then we feed those spikes to the microbrain chip, which does the spiking neural net processing.
So the first step here in this flow of information is done off chip, not in that chip that you've shown. So it's
yes.
done
The radar.
What
in this
forbids you
experiment, the radar is a commercial chip. The radar pre-processing is done in an FPGA, and then this is then done in the microbrain chip.
So what forbids you to integrate in your digital microbrain also the pre-processing directly
nothing.
To give away from the
it could be done, but the main drawback of these things is that you need to find this pre-processing specifically for your application. So you would need to make a chip that has the microbrain chip, some kind of programmable digital FPGA type of thing, and then one of our analog front ends that is event driven, like the level crossing A to D converter, and put that all on one chip for a given application.
Oh, that's great.
So
Okay, good.
that could be done, but in this case, we had the three pieces separately.
Okay, understood. Thanks for showing us. Also on the let's say more sparse sensing on slide 39, two slides prior, the event driven work that
Yeah,
you were about to publish in the upcoming
yeah,
ISSER conference in a few weeks. Basically, you have some predictions that having a power at the sub nanowatt range. I saw there
yeah.
in this curve. So the ADC, which used this nice innovation, uh, you were able to come down to 10 picowatts and even below that. No, can you show us how can you do that? Let's say, and is your deck able to work at such a low power levels like hundreds, 10 or 100 picowatt?
Well, I must say that this plot here was a simulation plot based on the model of the hardware. We then have built the chip, and it will be presented later on this month, later on in September. But basically, how it works is the following: you have the DAC that gives you the current position of where the signal is.
Right, and that's the amplitude
And
information that.
then that is the amplitude of where you were before. And then you have the input. And then there are two comparators. And when the input, say you are at this level, if the input changes with more than one LSB, then this comparator will flag that you have changed, the signal has changed with more than LSB compared to the current DAC level.
Mhm.
And then the control logic will start and change the DAC level. And it will also say, okay, here the amplitude has increased at this moment. And it will give that information with that time information. Same
Okay.
if the signal decreases compared to the current level with more than LSB, it will be detected by this comparator. And again, it
Oh,
will be
okay.
detected and it will send out that decrease in amplitude at this moment. So as long as the signal stays within plus minus 1 LSB
Okay.
of the current level, then the comparators see something at the input, they say, but no, nothing changes, and so nothing is produced at the output.
Right. Exactly. So basically, this tremendous ultra low sub nanowatt power is taking into account the fact that you have almost no event in most of the time. It's
Yes,
almost like a adiabatic computing, let's say, which is
yes,
terribly slow. Goes energy. The
yes,
energy per
and
computation
so
goes to zero if you just compute once every hour or so. say,
yeah,
let's
and
say.
so
Okay.
it depends, as you say correctly, it depends on the input signal.
Right. Okay. Yeah.
If
On
the
the
input signal is
bandwidth.
kind of
So
static. So that's
okay. So
why I
so.
started
Uh-huh.
saying here, you have to look at, for instance, medical applications, like the brain signal here, the third plot. You see that, yeah, there's a spike, but in between spikes, everything can stay within that LSB. And so
Right.
nothing will happen between spikes.
Right. So that's why the horizontal curve there is SER in log scale. So it's the
Yeah,
event rate, right? Okay. Okay.
yeah,
So yeah.
yeah.
Okay,
And
got it. So
the,
because
so
it's
we have to
frightening.
make
It's
such a plot.
frightening to work at pico levels and yeah, 10 or
Yeah,
100 picowatts. Then it's scary. So, but that's just a theoretical projection. If you have a signal that is very little event and has 0.001 hertz, let's say, bandwidth. Okay, got it. Okay,
yeah, and
okay,
it depends on the signal. So we generate these plots for different signals. I just
right.
showed one. If
But
we
taking
use,
taking an ECG, let's say, which has a certain bandwidth there of tens of kilohertz. Let's say you are talking about a nanowatt level. Let's say
yeah,
for the
yeah,
ECG.
yeah,
Okay, we're looking forward to the paper from European.
So the thing with all these machine learning, intelligence, and why can you have less power and so on, it's always very application specific.
Oh, indeed,
It's
indeed.
always very depending on the signals that you have.
Okay. Well, one last question, because we are taking too much of your time, but it's so exciting, the field. Now, you covered at the very beginning this very compelling idea of exploring, time encoding with the VCO. So, like in slide 18, let's say,
Yeah.
where you are trying to link. So this idea of having one way to encode from the two VCO. So the quick question is in this slide 18. If you were to do, let's say, a 28 nanometer, slide 18, if you were to do a 28 nanometer, let's say, ring oscillator, okay, with no trimming, where would we be sitting in terms of where we would be lying in the x-axis in phase noise if we had no access to trimming technique? So basically, would you be able to have a 40 dB more or less SNR
No.
without trimming? I would say so in light our students here on how difficult it is to do that with the basic proposition, which is originally the VCO with a ring oscillator as a very poor performance VCO.
This is true, but I did say that it's a ring oscillator, so it's a ring of digital inverter stages. I did not say that these inverters were minimum size. I did not
Okay.
say that. So by proper sizing, you can of the stages of the VCO, you can bring, for a typical design, you can bring the phase noise to around minus 90 dBc per hertz. So
Okay.
that would mean
Which is already a very sizable, a very good number.
Yeah. So
for
anything
this application.
90 minus 100, this is where we are. And then you can say, okay, let's assume minus 100, and you do an oversampling of 500, then you are here at 70 dBs.
Mm-hmm. Okay, so it has to be, let's say, a deep, many stages of the ring, and also a larger size to have
Yeah.
less mismatch.
More stages in the ring and many.
Okay.
Yeah.
Okay, so the students don't try to do that with 3 stages in your
No.
usually digital gate. We'll have an offer. You'll be all the way to the right here, more than minus 70. Let's say.
Yeah.
Okay.
By the way,
That's important because many students are listening to the talk.
Yeah.
And
by the way,
it's
we just
important.
published also in the IEEE Transactions on Circuits and Systems a paper on how to optimize the ring oscillator.
For
So
phase
the
noise.
entire paper is about how to optimize this ring oscillator.
Right, which is very important in this
Yeah.
case. Okay. I think we have already went over time. Thanks for your excellent presentation with so many results and so many exciting new ideas of those digitally assisted analog processing, which is key to so many architectures that you presented, implemented, and thanks for sharing with us your great experience of this enlightenment. As at this time, I would close the session. Thanks you very much, George, and now you have the word for your final say for our chapter members here.
Okay, I thank everyone for listening to my talk. I hope that I was able to excite you a bit about doing analog design still in these digital days, even though we do the analog circuits in a highly digital way, but it's still an analog function, and we are still needed in all these applications that I mentioned.
Right, you still extract
Yeah.
information from the real world, which is analog indeed.
which is
Thanks a lot.
yeah.
Thanks a lot, George. And it's always a pleasure to host and interact with you. It's an honor for our chapter here in Rio Grande do Sul, in South of Brazil, to host you. Okay, now
Okay.
Ricardo has a few announcements from the chapters. Ricardo, so you close the video. Bye bye.
Your microphone.
Your sound. You don't open your mic, please.
Yeah, I would like
Okay.
also to thank again to George for the very nice talk. Also to Sergio Bumpi for sharing the session. So next week, the talk that was scheduled due to some important reason was moved to November. And then till Monday, we are going to announce if you are going to have a replacement talk or no. Anyway, the week after, we are going to have a talk by Said Hamdoui from Delft University of Technology, talk about the design-aware test, the mean to win the war against unmodeled faults. And you have also in this YouTube channel the information about other talks that are already scheduled and with a flyer. So I hope to see you soon in the next CASS talk. Thank you to you all. And so we can close this.